Drawing the timing diagram of a finite state machine is straightforward once we know how to do the timing diagram for combinational logic and for flip-flops. In this case, we'll look at the ideal case, ideal combinational logic, ideal flip-flops, and get the timing diagram for an ideal finite state machine. We could do it given the Verilog code, we could do it given a physical picture of the hardware, and we can even do it given a state diagram, which is what we're going to be doing here. Here I have made up a state diagram and I've given the state representation that we'll use, not that it makes much difference for the timing diagram. We are given the clock and we are given the input to our finite state machine. We see that our input is just 1 bit, and so therefore our input's given by a single waveform here. If the input were 2 bits, we'd have 2 waveforms here, and so forth. Remember that the way the finite state machine works is that it transitions at the rising edge of the clock, so we just need to focus on the rising edges here. Internal to our finite state machine is the state, which is represented by the outputs of the flip-flops. Now in this particular case, we know that the state, because I've given the state representation, is 2 bits, and I could in principle have drawn 2 different lines here, one to represent bit 0 of the state and another wire here to represent bit 1 of the state. However, I will use the compact notation that ModelSim uses, and this denotes that I have multiple wires here, and I'm going to just draw in numerically the numerical value of the state. So I can draw in 0, 0, 0, 1 or 1, 0 into these to indicate the current state. Or to make it even more readable, I can simply put the letters A, B or C in there, and then you need to understand that, well, the actual values that go in here depend on the state representation. And so that's what I'm going to be doing here, putting in the letters A, B and C in here, remembering that it actually depends on the state representation. If we want a timing diagram for a realistic finite state machine where we have to take into account the delays of the logic circuits, etc., then the actual state representation is going to matter. But for this case, it doesn't matter. I can just use the state names in here and we all know what we mean. So we've got the clock and the in as inputs to our finite state machine. Internally, we have the state, and the output, being a more finite state machine, the output's just a function of the state. So when the state changes, the output will change. Let's assume that the starting state of our finite state machine is state A. Then at the first rising edge of the clock, we look at the input. We see the inputs are 0. We were in state A. We receive a 0, so we move to state B. So this becomes state B here. At the next rising edge of the clock, the input is a 1. We're in state B. The input's a 1, so we go back to state A. At the next rising edge of the clock, the inputs are 1. We're in state A. We therefore move to state C. And at the next rising edge of the clock, the inputs are 0. We're in state C. Therefore, we go back to state A. If you want to be very pedantic, then the state changes just after the rising edge of the clock to account for the infinitesimal delay in the flip-flops holding the state. And now from this, it's straightforward to write down the output, because the output just depends on the current state. We see that when we're in state A, the output's a 0. When we're in state B, the output's a 1. When we're in state A, the output's a 0. And when we're in state C, the output's a 0. And when we're in state A, the output's a 0. So we get this diagram here, and we're done.